In the equilibrium unit, you learned about the reaction quotient Q, and we're going to utilize that Q to predict if a precipitation reaction will occur. That'll be the first part of this learning objective, and then we will continue on by taking a mixture of many ions in solution and predicting who would precipitate first in that mixture. So if you calculate a Q for a solution, you can compare it to K and determine what state that insoluble salt is in. So let's say, for example, we've got the insoluble salt of lead chloride. And we know that this is the equilibrium process that we would consider. We know that K, which we call KSP, would be the concentration of lead times the concentration of chloride squared. But you could also talk about a Q. And a Q would be, okay, what's the concentration of lead right now, initially? What is the concentration of chloride right now? And let's square those. And compare that to the K value, the KSP value of that equilibrium. Well, let's start with the notion that we have an unsaturated solution. If it's unsaturated, that would mean that we could dissolve more if we had it to dissolve. Well, that would mean that we haven't quite gotten there and that the Q is too small. So anytime your concentrations that you have in solution of the ions of that salt gives you a value smaller than KSP, then you have an unsaturated solution. Well, certainly if it's saturated, you're right there at the point where they're equal to each other. When you will get a precipitate to occur is when it's supersaturated. If it's supersaturated, it is going to precipitate out. So this would occur when you have too much of the ions present. And if there's too much of the ions present and they need to come out of solution, how would Q compare to KSP? Well, it would be too large. So if Q is greater than KSP, you would get a precipitate to occur when you mix solutions together. If it's unsaturated or saturated, you would not get a precipitate to occur. So here is an example problem. I want to determine if a precipitate would occur, and the precipitate that could occur would be silver chromate, when sodium chromate and silver nitrate are added. Now what you would want to do is start by writing the reaction for that KSP. So Ag2CrO4 is the solid. You would have two Ag plus ions in solution, and you would have a CrO4 2 minus ion in solution, and that would be the equilibria. We know that the KSP is equal to the silver ion concentration squared times the chromate concentration. And that would also be the Q expression if they were all initially. And that's what we're going to figure out. What are the initial concentrations of those? Now you will not come up here and take this and this number directly and plug them into those concentrations, because we have got two separate flasks, and let's consider here. We've got, or beakers. We've got one beaker that has in it 250 milliliters of 0.33 molar NaCr2O7 or Na2CrO4, sorry. In other words, since this dissociates, it has a 0.33 molar solution of the chromate ions in solution. Okay, that's one beaker. In the other beaker, we have got the solution that contains the silver nitrate. And there are 250 milliliters of this solution, and it's 0.12 molar AgNO3. What I need to plug into my expression is Ag, so it's 0.12 molar Ag plus. And then we're going to take those two and we are going to mix them together. So we're going to pour them into a larger beaker, and there's going to be in this beaker 500 milliliters of solution. And what that does as we add those together is it's going to dilute down the chromate ion concentration because I'm adding the other solution. And it's going from 250 milliliters to 500 milliliters. And I'm going to dilute down the silver ion concentration because I'm adding the other solution and it's going up to 500 milliliters. So let us calculate the silver ion concentrations after these have been mixed, and after they've been mixed and before they've had a chance to react. That would be the initial concentration of silver in this beaker down here. Well, I'm going to be considering a dilution, so it's going to utilize M1V1 equals M2V2. So the silver ion concentration would be, that I want to put in here, would be the M2 of this equation. M1V1 equals M2V2. M1 is 0. I'm looking at the silver concentrations and volumes here. Okay, so it's 0.12 molar. I have 250 milliliters of it. M2 is what I'm trying to determine. V2 is 500 milliliters. So M2, which is the silver ion concentration initially, after I've added it to that beaker, is going to be 0.06 molar. Now we'll do the same thing for the chromate and the other beaker. For this, I'm going to consider these amounts. And I'm going to realize that the chromate concentration would be M2 in this dilution. M1V1 equals M2V2, where M1 is, consider that beaker on the left now. The M1 started out as 0.33 molar. V1 is 250 milliliters. M2 is what I'm trying to determine. And V2 would be 500 milliliters. So M2 in this dilution would be equal to 0.165. Now I'm carrying an extra sig fig there, but that's okay. That's the concentration of the chromate. So now at this point, I'm going to take these two amounts, the concentration of the silver initially, the concentration of the chromate initially, and I'm going to plug it into my Q expression and determine Q. So Q would be 0.06, and I'd have to square that number, times 0.165, and that will give me a value for Q equal to 5.9 times 10 to the minus 4. Now I'm ready to compare that Q to the KSP. Here's the KSP. We see that Q is much greater than the KSP. We have too much ion in solution, and whenever Q is greater than KSP, it needs to precipitate to bring that value back down. So will it precipitate or form? The answer is yes. Now we're going to utilize this concept of precipitation to talk about selective precipitation. And it's going to use the different solubility properties of salts to separate out ions from solution. Let's start by considering this. You're going to look at this solution, and I have added some chloride ions, bromide ions, and iodide ions. Now, of course, there's going to also be some kind of cation in there. But maybe it's sodium chloride, sodium bromide, and sodium iodide that I've dissolved into a solution. And in this solution, I'm going to start adding silver ions, slowly, drip by drip. And the question is, if I compare the KSP values that I have given down here, which one of those three ions would precipitate first? If you selected AGI, then you're correct. Silver iodide would precipitate first. It has the smallest KSP. Ooh, that doesn't look like smallest to me. There's a T. It's the smallest KSP. And so it would precipitate first. It's the least soluble of the bunch. Now, once you've decided what's going to precipitate first, you could then figure out, well, how much silver would be needed to make it precipitate. So I've expanded this question a little bit by giving you concentrations of those three ions. Now, we know that the iodide is going to precipitate first, especially since I'm starting with the same amount of all those. Now, if we weren't starting with the same amount of all those, there could be trouble. But we are starting with the same amount of all those, and I'm adding the silver, and the silver iodide would precipitate first. So I'm going to use my KSP value, expression for the silver iodide. It's the silver concentration times the I minus concentration. I'm going to put in the KSP for silver iodide. It's 8.3 times 10 to the minus 17. I am going to put in the iodide concentration that I have here, 0.010 molar. And that would give me a silver ion concentration equal to 8.3 times 10 to the minus 15. So that concentration of silver is all I would need in solution to start the precipitation of the silver iodide. At that point, the bromide and the chloride would not precipitate at all. And that's not very much. So let's expand this even more. Now, the iodide's precipitating, and I keep on adding. And eventually, the next ion in line to precipitate, which is the silver bromide, is going to join the precipitation ranks. So I want to know what would be the concentration of I minus when the silver bromide just begins to precipitate. So let's think about what's being asked here. First thing that starts to precipitate is the AgI. It precipitates by adding a little bit of silver. Add a little silver, it keeps precipitating. I add a little silver, it keeps precipitating. Eventually, my concentration of silver is going to increase to the point that the silver bromide is going to precipitate. Is this a point where there's still a lot of iodide in there, or have we gotten rid of most of the iodide? We can see this with this problem. Okay, so we're going to take that second equilibrium. The KSP for silver bromide would be the silver concentration times the bromide concentration. So KSP for silver bromide is 7.7 times 10 to the minus 13. That is going to allow us to figure out how much silver is needed to precipitate this bromide. So the silver concentration that's just going to get this silver bromide to precipitate is going to be 7.7 times 10 to the minus 11. Okay, so as soon as I get the concentration of silver to that amount, finally the silver bromide is going to precipitate. Remember what it was on the other one? With the silver iodide, it was only 8.3 times 10 to the minus 15. Okay, that's what got the first one to precipitate. Now I've got to get this concentration of silver up to 7.7 times 10 to the minus 11. And then it begins to precipitate. Now once it begins to precipitate, we can now answer this question. What would the I minus concentration be? Well, let's go back to our initial KSP for silver iodide. And let us now put in this silver concentration that we got from here into this equation. Now the KSP is still, of course, 8.3 times 10 to the minus 17. We have upped our silver concentration now to 7.7 times 10 to the minus 11. That's when the silver bromide starts to precipitate. And we can see, well, how much iodide would be in there. So if we divide both sides by 7.7 times 10 to the minus 11, we will get an I minus concentration of 1.1 times 10 to the minus 4. So we started out with 0.01 molar I minus, and the silver iodide precipitates. Its concentration will get all the way down to that value, 0.0001, before the second one starts to precipitate. So we've gotten a lot of it out of solution before the silver bromide precipitates. So this is the end of our learning objective 13, in which we're looking at precipitation reactions. Will they occur? We're looking at selective precipitation. This is also the end of our aqueous equilibria unit. And historically for students, this is a very challenging unit. So make sure you watch and rewatch the lessons. Make sure you spend time examining the practice problems where I am working through problems, and really work through those problems that we have assigned to you. In every case, you have to write your own reaction, and I think for most students that's the challenge. Think about what's occurring in solution. What do you have? Is it an acid? Is it a base? Is it a mixture? Do you have a insoluble salt that you're considering? And how do you write those? So make sure you're really spending the time working problems, because there's just no substitute for that with this unit.